For unsymmetrical dienes, the major product will depend on the location of the electron donating group. In the case where the electron donating group is on an inside carbon, the 1,4 product will predominate. When it is on an outside carbon, the 1,2 product will predominate. And to understand why this happens, we'll just have a look at the resonance structures. So firstly, the case where the electron donating group is on an inside carbon, and I'm having it react with an alkene, and the electron withdrawing group is an aldehyde. And I chose this because it's easier to draw in a resonance structure so people can understand it visually easier than some other electron withdrawing groups. It would be a little bit messier with that kind of resonance structure, but anyways. The electron donating group donates a pair of electrons. The electron withdrawing group will withdraw a pair of electrons. So drawing the resonance, here the donating group gives a pair of electrons. Now there's a new bond here. It's given up a pair of electrons to this carbon. This set of electrons here now is superfluous to this carbon, so it goes to the other carbon, creating a carb anion, negative charge. Looking on the alkene, the electron withdrawing group takes a pair of electrons. This oxygen will take a pair. Now this carbon is deficient and it will get its pair of electrons from this double bond. This double bond will shift over here, as we've seen them do many times before, and this creates a carbocation, a positive charge. So now it's easy to see that this charge matches up with this, and it's therefore likely to react in this way as opposed to the crisscross manner, which would give the 1,3 product instead of the 1,4. But since these charges are like charges and are going to attract each other, it's easy to see why this would be more predominant than this crisscrossing pattern. And it's the same kind of thing when the electron donating group is on the outside as well. The electron donating group donates a pair of electrons. Now this carbon has extra electrons, so it gives up this. It basically just passes this electrical charge down all the way to the N carbon, and it becomes a carb anion. So this is a strange one when first learning this, because intuitively, before even looking at what the answer is when thinking of a reaction like this, you almost want to say logically, well, this carbon is right next to the donating group. Should it not have more negative charge? And I'm not going to go into why that is. I'm not saying I'm not sure, but I've never seen it written in a book anywhere why that is, but I have my own theory on it. I think it has to do with the shape of the orbitals, but we'll go into that another time. But just know that in these type of reactions, this is what happens when people have done this in real life. And what they found with these different kinds of reactions is not only are these two things generally the major product, often they're the only product. That's how much a stronger of a reaction it is comparing to the crisscross one. So anyways, this donates a pair of electrons. There was a double bond here, now this goes over here, now there's a double bond here, and then this double bond is no longer needed on this carbon, so it goes over here, so it creates that. And this is exactly the same thing as this up here, so we don't need to go over that again. Carbocation, opposites attract. The crisscrossing pattern is not likely to occur. Since these attract, it's going to create the 1,2 product. And that's why we have the 1,4 and 1,2 products. If there's ever any doubt, just go ahead and draw the resonance structure. More often than not, it's going to give you the right answer, and if you're interested, I probably will do an explanation on why I think that this is not the more reactive carbon than this one, although someone would probably think that it would be because it's right next to the electron donating group, but I'll do that some other day. Check it out if you like.